Hello, everyone, and welcome to your enzymes presentation. So in our first unit of biochemistry, we talked about how our molecules of life help us to survive. Our four major macromolecules were carbohydrates, lipids, proteins, and nucleic acids. Today, we are going to be talking specifically about a special protein called enzymes. Enzymes are helper protein molecules. And we're also going to talk about what factors actually affect their activity and how well they do their jobs. So I always like to include our standards. So this comes from standard 4.1.3, which says explain how enzymes act as catalysts for chemical reactions. So we're going to talk about how enzymes are catalysts and what exactly a catalyst is. After this presentation, you will be able to demonstrate the link between shape and function as it relates to an enzyme substrate complex. So you'll be able to tell me how that enzyme and substrate actually interact. You'll be able to explain the effects of environmental factors like temperature and pH on enzyme efficiency. So how well does the enzyme do its job in certain situations or environments? And lastly, you'll be able to identify the role of enzymes in chemical reactions in organisms. So what exactly does this particular enzyme do in this organism or in this part of the body? So let's think about this for a second. Maria loves ice cream, don't we all? When she goes to Cold Stone, her favorite combination is sweet cream, vanilla, and Oreos. Sorry, I spelled that wrong. With the gummy worms on top, of course. But it never fails. Every time after she eats her ice cream, she has bloating, gas, and diarrhea. All milk and dairy products typically contain a sugar called lactose. So how do you think Maria's body is reacting to the lactose? How do you think Maria's reacting, or how do you think her body is reacting to this carbohydrate? So enzymes are important proteins. You might not realize it, but your body actually runs on chemical reactions. When you're breaking down food, when you're making energy, and when you're building the molecules that actually make up your body, these are all chemical reactions, and all of your chemical reactions need enzymes. So Maria's body actually can't break down the sugar or lactose in the dairy products because her body doesn't produce enough of the enzyme lactase. So lactose intolerance is actually a disease that affects many individuals in the world, not just Americans, not just North Americans, South Americans, everyone. And it affects a lot of people, but it's the inability to break down that sugar efficiently. And so bacteria and water break down the sugar inefficiently and cause fermentation. And then that gas builds up and it just makes it for a whole uncomfortable experience. However, thanks to modern science, Maria can add a liquid or powder lactase enzyme to break down to her drink or things like that to break down that lactose. So what are catalysts? We were talking about explaining how enzymes are catalysts, but what are catalysts? Well, catalysts are molecules that speed up chemical reactions, so it makes them go faster. So let's look at this graph right here. You're never gonna get away from graphs. Sorry, just not gonna happen in my class. This is science, come on. So let's look at this graph and let's understand the basics of what this graph is trying to tell us. Graphs are just detailed pictures that tell you all the who, what, when, where, and why of an experiment. I love graphs. They're like a snapshot picture. So let me get my annotation tool out and explain a couple of things or refresh a couple of things. So graphs always consist of an X and a Y axis. The X axis is the horizontal axis right here, and it always shows the independent variable. So this is my X axis. It always shows my independent variable. My y-axis is always vertical, straight up and down. That's my y-axis, and my y-axis is my dependent variable. And so On my two axes, my independent variable is the variable that we're actually manipulating, right? The variable that we're actually changing. So the progress of the reaction is what we're seeing how it's going. That's what's changing. The progress of the reaction, whether with an enzyme or without an enzyme, is what we are observing changing, right? And the dependent variable is what is changing depending on the independent variable. So the amount of energy the amount of energy needed or expended in this reaction is dependent upon the progress. So how far it goes, okay? Titles always help a graph too. So this graph is showing the amount of energy expended over the course of a reaction when there is no enzyme and when there is an enzyme. It's showing the speed of the chemical reaction. So how fast the chemical reaction is going with an enzyme and without an enzyme. The dotted line shows with the enzyme. The solid line is without the enzyme. So any chemical reaction, let's use this graph and say that we're trying to break down some food, right? With an enzyme, we can break down that food much faster than without an enzyme. But how? How does that actually happen? How do we actually do that? How do enzymes actually speed up the reaction? Well, all reactions actually have an activation energy. And that's the energy needed to start the reaction. Think about activation energy. What does it mean to activate? It means to start. So the activation energy is the amount of energy you need to start. The amount of energy you need to start your car is the activation energy for you starting your car. The amount of energy I need to walk to my car and go start it is the activation energy. So enzymes actually lower this activation energy. So they lower the amount of energy you need to get started. They lower the amount of energy you need to break down this food and start breaking down this food. So let's look at this graph over here. With an enzyme, the amount of energy we need to start this reaction is a lot lower than the amount of energy we need when there is no enzyme. That is what this graph is telling us. Without the enzyme, look at that. We have to climb a steeper hill versus without an enzyme, I don't need as much energy to get going. Enzymes are specific, meaning that they are shape specific. That means that an enzyme can only bind to one substrate. That's why we have hundreds and hundreds of enzymes. This is why we have hundreds of different enzymes. Okay? So enzymes are specific, and because they are shape specific, we have only one enzyme that's able to bind to one kind of substrate. So that's why we have hundreds of different kinds of enzymes so they can bind to their own special substrates. And their shapes must match. Shapes must match. The reaction for enzyme A is going to happen because they fit. This is our substrate. This is our, sorry y'all, this is our substrate. And this is our enzyme. Our substrate fits in the enzyme. However, look at this one over here. These shapes don't match. This is a circular shape and that's more of a diamond shape. And so if the shape doesn't match, then guess what? The reaction's not going to happen. They don't fit, so it's not going to happen. Shapes must match on the enzyme and the substrate. And so scientists actually use a lock and key model to explain this. They said, we can actually connect the way that enzymes and substrates connect to the way that locks and keys connect. So because of their shapes, only one enzyme fits to one substrate. So we have bunches and bunches and bunches of different enzymes that all break down their own special and specific substrate. So just like only one enzyme fits with one substrate, one key can fit into one lock. Does the key to my house fit to the key to your house? Does my car key crank up your car? No way. So enzymes are shape specific and they use the lock and key model to explain that. Another postulate or another theory or another way that we can remember that enzymes are shape specific is that they're normally named for the substrate they bind to. So out of these hundreds of different enzymes with all their special substrate they break down, they're even named after them. So they're all pretty much married. Mr. Walker is married to Miss Walker. Mr. Johnson is married to Miss Johnson. Mr. Stotts is married to Miss Stotts. All right. So their enzymes are typically named for the substrate they bind to as well. All enzymes end in ACE, A-S-E, or majority of enzymes. Majority of enzymes end in ACE, A-S-E. So here are some examples. Oh, I'll give you this little tidbit. While majority of enzymes end in ACE, majority of sugars end in OS. So while enzymes end in ACE, sugars end in OS. Most sugars, most simple sugars, I'll put it out there like that. Most simple sugars end in OS, but most enzymes end in ACE. So here are some examples. Sucrose is the table sugar, it's table sugar. And sucrose, we know it's a sugar because it ends in what 3 letters? It ends in ose. And sucrose is broken down by what? If all enzyme names end in ACE and they are named for the substrate they bind to, sucrose is the substrate it's breaking down, yes? So the first part of the name is sucra, I guess, because it's named for the substrate it's binding to. And the names end in ACE. So put ACE here, sucrase. So sucrose is broken down by sucrase. There it is. Proteins are broken down by, all right, let's do it again. So enzymes, again, are typically named for the substrate they bind to. So if they're named for the substrate they bind to, then we take the first part of the substrate, protein, and it says the enzyme names end in ACE. So then we put ACE on the end, protease. There it is. Okay. So what do you think lipids are broken down by? Enzymes are typically named for the substrate they bind to. So take the first part of the substrate name and put ACE on the end. So lipids are broken down by lipases. Good. So enzymes are specific. Let's talk about the enzyme substrate complex. These are available on your notes, but I want to talk about each step. So the first step is that the substrate, which is what the enzyme is breaking down or building together, because remember, enzymes break down your food and they also build up the molecules that make up your body. So the substrate, what the enzyme is acting on, enters the active site of the enzyme. So the enzyme has an active site, this opening right here, where the substrate snugly fits. Step 2 is where the enzyme substrate complex is made. A complex is when there is a molecule or a system that is made up of more than one part. Complex means that there are more than one, or there is more than one moving part. And so the enzyme substrate complex is when your enzyme and your substrate are snugly fit together in that active site. Your substrate is fitting snugly into that active site. The enzyme changes shape just a little bit so that the substrate can bind and fit perfectly. You see how it was a kind of an oval shape, but now it's like a perfect circular shape around. So think about putting a hand in a glove, right? Step 3, your enzyme, between step 2 and step 3 is where the reaction takes place. And now your enzyme has either broken down or put together the substrate to create products, but they haven't left the active site yet. The enzyme hasn't released them yet. Step 4 is when the products actually leave the active site of the enzyme and the enzyme is ready for another reaction. Okay? Please note, this reaction can happen both ways. Meaning, we can begin, and this is step 1. And this is step 2. And this is step 3. And this is step 4. So not only can we put things together, not only can we bind things, but we can also break them. So this, we broke up this substrate. But we could also, enzymes can also bind the substrate. So they can actually bind the substrate and put it together and release it into a larger molecule. Okay? Enzymes are reusable, meaning that enzymes are not changed by the reaction that they actually help. Throughout the whole process, the enzyme did not change. The substrate is what changed into the products, but the enzyme did not change. The only time it changed shape was when it could snugly fit, like holding your mom's hand or holding your boyfriend's hand or your girlfriend's hand, right? When you got your hands locked together and they snugly fit. But other than that, the enzymes didn't change. So we actually don't need more than a few enzymes. Since they're reusable, we don't need more than a few in our body. Like, of that specific enzyme. Let me clear that up. So there are specific enzymes for specific substrates, and there are hundreds of different substrates. However, there only needs to be a few enzymes per substrate. All right? So enzymes, we learned, are catalysts. They speed up reactions by lowering that activation E, lowering that energy to get started. We know that they're specific to a particular substrate, which is what the enzyme binds or breaks, right? We know that enzymes are reusable. We know that enzymes are reusable, meaning that we don't need many of them per type of substrate because they don't change shape. Now, let's move on. What happens though, unless they're denatured? What happens if they change shape? What happens if they change shape? Enzymes are fragile. They're affected by temperature and pH. What happens if those enzymes change shape? We know they work and we know how they work, but what happens if they change shape? So we said that enzyme shape matters, but what happens if they change shape? Let's think back to the lock and key model, where a specific lock fits to a specific key, just like a specific enzyme fits to a specific substrate. But what happens if you bend the key? If you bend the key to your door, your key will no longer fit in the lock and the lock won't be able to open. So if the shape of an enzyme changes, it can't fit with its substrate. So the reaction actually can't happen. When an enzyme changes shape and the reaction can't happen anymore, this is called denaturing, or the process of becoming denatured. What causes an enzyme to become denatured, to be taken out of its nature? If we were to break this word down, denature. Denature. D means to take out. And nature is your original state or your original being. So to be taken out of your original state, what is causing this to happen? What is causing this enzyme to be taken out of its natural state? Well, there are two factors that actually affect enzyme action. Two factors that can actually affect how well the enzyme is doing its job. They're temperature and pH. So let's start with temperature. All enzymes have an optimum temperature, or a best temperature, or a best condition that it works at. The optimum is the best situation. So think about your optimum temperature of working in your room. That's what, about 72 degrees, 73, at the highest 75, right? That's the best conditions for you to work. Well, different kinds of enzymes have different kinds of best temperatures that they work at, best conditions that they work at. Just like you have a best condition that you work at, and there's a best condition that your friend works at. So let's look at this enzyme, for example. This enzyme, let's say this enzyme works best at 37 degrees Celsius, because let's say we're talking about an enzyme in the human body. Let's say we're just talking about a particular enzyme in the human body. And this enzyme works best at 37 degrees Celsius or 98.6 degrees Fahrenheit, because that's our normal body temperature. That's our optimum body temperature. So this particular enzyme we're going to be talking about works best at this temperature. It's all due to its environment that it's in. And so here's another graph. This graph actually shows the activity of this particular enzyme in the human body. All right, so here the graph says, or here the graph shows us 3 different points. Let's remember, we make sure we know what we're looking at. Our x-axis is the independent variable, right? That's what we're manipulating over time, and that's the temperature and the rate of the reaction. So how efficient and how fast the reaction is going, how well the reaction is going, is on our y-axis. And that is our dependent variable. And so remember, the rate of the reaction is dependent on the temperature, right? And what temperature that the reaction is happening at, what temperature this enzyme is actually working in. All right. So that's what this graph is telling us. So let's look at these 3 points on the graph and talk about what's happening in these 3 points in the graph. So the first point is A. So as the temperature increases from 0 to 37 degrees Celsius, the enzyme activity is increasing. How do we know that? Because let's look at our graph. It has a positive slope. Right? It has a positive slope. So it's increasing. So as the temperature increases, so it goes from 0, super cold, to about 37 degrees Celsius, the activity is increasing. Now, how do we also know where the temperature, what the temperature was from 0 to 37? Because we were able to follow the line. And then when we got to where the activity plateaued or stopped increasing, what did we do? We drew a line down to where that point would be on the x-axis, or on the x, or to figure out what temperature. Okay. So the graph peaks. Let's look at B. So as the temperature increases, the enzyme activity is increasing. All right. As the graph peaks at 37 degrees Celsius, how do we know that was 37 degrees Celsius? Because we looked at the top of the graph and we drew our little line down to our x-axis of where it would land on our x-axis. Okay, the graph peaks, or is at the top, at 37 degrees Celsius. So this is our optimum. So where the graph is highest, where the line is highest, that's where the optimum is, where the line is highest on a graph. So that's the best temperature that this particular enzyme in the human body is working. Okay. Let's look at C. As the temperature continues to climb, so as the temperatures climb greater to higher heights than 37 degrees Celsius, the enzyme activity actually decreases. So the enzyme activity, once it gets too hot, the amount of work that the enzyme is now doing is drastically decreasing or going down to the point where it altogether just stops, because the temperature is most likely too high now. The best temperature, I told you I work best here. So why are you trying to go above and beyond? That's the way the enzyme is talking. Okay, so that means that 37 is the optimum temperature. That peak, that highest point, is the optimum temperature or optimum condition for that enzyme. Okay. So past 37 degrees, again, past that optimum, the enzyme starts to denature and change shape. This is why the enzyme is no longer working. This is why the graph of enzyme activity is dropping, because the enzyme has now changed shape. And if the enzyme changes shape, there are less reactions, because shapes must match. And if the shapes don't fit anymore, there are no reactions happening. Okay. So let's look at this example and let's answer these 3 questions together. The first thing we have to look at is, what is this graph telling us? So this graph is telling us the effect of temperature on the efficiency of this enzyme's activity. All right. So what is the optimum temperature of this enzyme? We have to go to the tippy top, the highest point, the peak. So what is the highest point? What is the peak? Circle it. Now draw a line down from the tippy top all the way to where it intercepts on the x-axis. So come down. I'm speaking math to you, ain't I? And good. So it's 37 degrees Celsius. All right. So the enzyme works best at this temperature. We can see that because this is where the most reactions is happening right now. This is where the most reactions is happening. Or excuse me, most reactions are happening. Okay. So the more reactions it does, the more efficient it is. So the efficiency, boom, we got that right here. So it was 37 degrees Celsius. Okay. The enzyme activity is increasing between what two temperatures? So between what two temperatures is enzyme activity increasing? So it's getting higher and higher. Good. From zero to 37. How do we know that? Because we saw the positive slope, the increase of activity. So there's more activity happening as we continue on between the temperatures of 0 and approximately 37 degrees Celsius. Okay. And my last question was, at what temperature is the enzyme denatured? So what does it mean to be denatured? What does it mean? It means that it changed shape. So it no longer works. It changed shape. Okay. So at what temperature is the enzyme completely denatured? It no longer worked at all. It changed shape. It didn't work. It's not working. The rate of the reaction is extremely low. The rate of the reaction is extremely low. It's down here towards the bottom. So we follow that and look at that. Boom. And what temperature can we say? What temperature is this? Estimate for me. About 55 or 56, right? So we would say about 55 degrees Celsius. Okay. So pH also affects enzyme action or the efficiency of enzyme activity, right? So what is pH? pH is a scale from 0 to 14 that actually measures acidity. So how acidic or how basic something is. So here's our scale, 0 to 14. And the lower the number, the more acidic that solution or the more acidic that it is. Okay. So the lower equals lower numbers equal acids. Okay, so the lower the number, the more acidic. So some acidic foods or solutions or things or liquids are orange juice, soda, and vinegar. So have you ever had like some McDonald's Sprite and it hit your throat, bro? That's the acid, that carbonated drink. Vinegar, super acidic. All right, 7 means that it's neutral. So 7, the pH of 7 is a neutral pH. So things like water, harmless. And your basic solutions or basic things or things like, or basic molecules or things like soap, compounds, soap, baking soda, and bleach. So I used to think that bleach was an acid, but it's actually a base. And so baking soda is actually basic. So the higher numbers, so the higher numbers are bases. Okay. So if anyone's ever done an experiment where you mix vinegar and baking soda and it bubbles up and then it settles at a neutral solution, that's because you mixed an acid with a base. So that's pretty cool. I had a question and I wanted to answer this question really quickly. What does pH stand for? And pH stands for the amount of hydrogen ions in a solution. So it's actually the concentration of hydrogen ions in a solution. So the more hydrogen ions a solution has, the more acidic it's going to be. So watch out. All right, cool. So now let's talk about how pH can affect enzyme activity, because we also have a natural pH in our bodies, like natural pHs all over our bodies and different pHs all over our bodies. And so all enzymes have an optimal pH as well. So not only do these hundreds of enzymes that have their specific substrates they break down and bind and things like that, not only do they have perfect conditions that they work at for temperatures, but they also have perfect and different pHs that they work at, because all these enzymes, they do work and they have to have the perfect conditions to do their work. So for example, let's use salivary amylase as our enzyme. So salivary amylase is actually an enzyme in our saliva, or our, what's another name for saliva? It is spit. So in our spit that digests a starch called amylose. Let's figure this out. Ose, it ends in ose, so it must be a sugar. And we know sugars are what kind of macromolecule? Carbs. So we have enzymes that actually break down carbs. And amylase is a specific enzyme. Amylase, ACE enzyme, is a specific enzyme that digests a carb in your, that digests carbs called amylose. So pretty cool. So your saliva is a pH, or has a pH, or possesses a pH of 6.5 to 7.5. So what would the optimum pH be of amylase, salivary amylase, working in your saliva? What is the optimum? What is the middle, right? What is the best condition? So the optimum pH for salivary amylase would be about 7, because if I were to draw a quick graph, right? If I were to draw just a quick graph, right? We put pH on our x-axis, 0 through 14. And then we put rate of the reaction, right? And let's say this was 7. This is the graph, and this is what it would look like. And you have 6.5 to 7.5, 6.5 to 7.5. Where would my optimum be? Remember, it's my peak, my very top, and I draw my line down, and there is my 7. All right. Your optimum will always be the top part of the graph, the middle, the best part of the graph. Not the middle, but the peak of your line, the peak of your activity. All right, so this is a graph for salivary amylase. Here it is. Here's the graph that I just so poorly drew out for you 2 seconds ago. All right, so the tippy top of the graph always shows our optimum. That's our peak. That's our optimum. That's our peak, our optimum, our peak. Okay. And so when the pH is below 7, right? So when the pH is below 7, the enzyme denatures, so the activity is lower, right? Remember we said we have best conditions that we work at. And so when the activity, when it's too acidic, when the environment is too acidic, amylase is not working correctly. It changes shape because it's too acidic. It morphs. It's like, oh my God, I can't do this. And so it can't do any work. The same thing goes for when the pH is above 7. So if it's too basic, if the environment is too basic, amylase won't work because the shape is going to change. It's going to denature. So let's do this one together. Let's look at pH. Do both enzymes work best at the same pH? Let's look at this graph really quick to make sure we understand what this graph is. Here's our x-axis, which is our independent variable. And here's our y-axis, which is our dependent variable. And so this graph is basically telling us the rate of activity, so how well the enzyme is breaking down its molecules or building its molecules based on the type of pH that it's in, or based on the acidity of the solution that it's in. Okay? So do both enzymes work best at the same pH? How do we know whether an enzyme works best? What do we look for? Right, we look for the optimum or the peak. So if we're looking for the peak, do both enzymes work best at the same pH? Do both enzymes have the same optimum peak? Do both enzymes have the same peak? No, both enzymes do not have the same peak. So that means that these two different enzymes work best at different places or at different pHs. At what pH does each enzyme work best? How do we figure that out? Okay, so we go to the peak. We go to the peak, and then what do? We draw our dotted line down to where it would cross the x-axis. So gastric protease works best at what pH? Good, 3. What does intestinal protease work best at? Okay, so we go to our peak and we do our line down to where it would cross the x-axis. What is that? About a 9. So intestinal protease works best at a 9. All right. And so my last question is, what would happen if I placed intestinal protease enzymes in an acidic solution? So the first thing we have to know is where intestinal protease enzymes, where they work best at. So where do they work best at? Intestinal protease enzymes, that's the solid line, works best at, we said, 9. So they work best at the pH of 9. That's what we just said in our last question. Now it says, what would happen if I placed intestinal protease enzymes into an acidic solution? So what does it mean for a solution to be acidic? Are they lower numbers or higher numbers? Are acids lower numbers or higher numbers? Good, they're lower numbers. So if they're lower numbers, what would happen if I place intestinal protease enzymes, so enzymes that work at, as we see, a higher number best, into an acidic solution, so working at lower numbers? What would happen? Exactly. The enzyme, use your vocabulary words, the enzyme would become denatured. So it's not enough just to say that the reaction wouldn't happen or the enzyme won't do any work. It's not enough to say that. I need you to tell me why. Why would the enzyme not do work? Because it's denatured. And the graph further supports us on that. How? Because The graph further supports us on that because look at this. Look at intestinal protease and look at where the activity is 0 at lower pHs. It's already not working at 4. So we already know that in acidic areas, it won't work. So the graph further supports our answer. All right, so we know that enzymes can be denatured, and that means that they change shape and no longer work. And they're affected by temperature and by pH, the amount of hydrogen ions in that solution. Here are some more supplemental videos that you guys can watch if you want to know a little bit more about how enzymes lower their activation energy or about why you can't live without enzymes. And thanks for coming to my lecture.